Hi, I'm Fiona. I will be doing Khan Academy 18.1 from the Thermodynamics and Free Energy. So first, the hydrogenation of ethene was determined to occur by way of a multi-step mechanism. Given the reaction steps below, determine the sequence of reactions that yield the equation above, indicate whether each step is endothermic or exothermic and whether the products are more or less ordered than the reactants for each of the individual steps, as well as the overall reaction, and calculate Gibbs free energy in the product at 185 degrees Celsius and indicate whether at this temperature the reaction occurs spontaneously. So as we go through these, we'll determine first, how do these reaction steps become this overall reaction? Second, in each of these reaction steps, are they giving off or taking in heat, and are they becoming more or less disordered? So we'll be looking at entropy there. And third, we're calculating Gibbs free energy to determine whether the sign of delta G and whether the reaction will go on its own or would it need outside energy. So first, let's look at A. To do this, we're going to try to match the coefficients of each of these reaction steps to the coefficients of the overall reaction by multiplying the whole reaction step by a coefficient. We also need to make sure that if in these reaction steps, what we need is in the reaction or the reactants, it needs to be in the product. So we'll have to reverse the reaction. So first one, we multiply by 1/2 to match this C2H2 coefficient. Second one, we multiply by 1/2 to match this C2H6 coefficient to this one over here. And the last one, we multiply by 2, again to match the coefficient. Now you'll notice that in this one, C2H6 is in the product, or in the reactants, and here it has to be in the product. So we're going to reverse. So let's write out each of these after these multiplications and make sure we get all those coefficients, even if they're fractions. If they are all set up, now we're just going to double check that these are actually the reaction steps. We're going to try to cancel out all of these extraneous reactants and products, and we're also going to make sure that all of our coefficients match these ones above. So we can cancel oxygen. There's 7/2 on this side, 7/2 on that side. You have to add up these two. And here, 2 carbon dioxide, 2 carbon dioxide, and all of the waters cancel, and you are left with this overall reaction. So yes, these are the steps to get to this overall reaction. Perfect. Part B, indicate whether each individual step is endothermic or exothermic, and whether the products are more or less ordered than the reactants for each of the individual steps, as well as the overall reaction. So first, let's start with this first part. Are they endothermic or exothermic? To do this, we need to get the delta H. And we look at what we did to each of these reaction steps, and we're going to do the same thing to delta H. So we multiplied this by 1/2, we multiply that by 1/2. Same thing here, except this is a negative 1/2, because remember we reversed the direction. And that, in this part, comes out as changing the sign of the delta H. The last one, we multiply by coefficient. Now, the first one is endothermic because this sign is negative. Delta H is negative, therefore, sorry, I said endothermic, I meant exothermic. First one is exothermic because delta H is negative. Second one is endothermic because delta H is positive. Third one is exothermic because delta H is once again negative. So delta H overall, by simply adding up these steps, we add them, we get negative 312 kilojoules. That is exothermic because it is a negative delta H. Perfect, we've determined whether each individual step is endothermic or exothermic, and also the overall. So now let's move on to the part that is dealing with. So for this, we're going to add up the entropy of each of these reactants and products. So it's going to be products minus products minus reactants. I pointed the wrong ones. So while doing this, you have to make sure that the products, if it's a product, it's negative, because remember it's product. If it's a reactant, it's negative, because remember it's products minus reactants. So there you go, negative, negative, making sure you're getting those coefficients there. And entropy is going down because this is negative. The same second one up, entropy is going up because this is positive. It's negative, entropy is going down. Now, if entropy is going down, that means that disorder is decreasing, which means order is increasing. So the products are more ordered than the reactants. Here, entropy is increasing, meaning disorder is increasing, and the products are less ordered than the reactants. And the last one, same reasoning as the first one, entropy is decreasing, therefore disorder is increasing, and the products are more ordered than the reactants. So overall, we just all up, perfect, and we come up with an answer of negative 233.1 joules per Kelvin. Entropy is decreasing, and the products will be more ordered than the reactants. Lastly, we're going to calculate Gibbs free energy. So here we are given 185 degrees Celsius. We have to use delta G equals delta H minus T delta S. Delta G here is heat of reaction, delta S is entropy, T is temperature, delta G is exactly what we're looking for, Gibbs free energy. So we're given that 185 degrees Celsius, we need to Kelvin. So we add 273 to get 458. Negative 312 kilojoules minus 458 Kelvin. We're just plugging in these values. Remember, this negative 312 kilojoules is what we calculated before in part B. And so then we look at that entropy that we calculated in part B, negative 233.1 joules per Kelvin. And we have to remember that that is joules per Kelvin, so we convert that to kilojoules. We multiply those out and we get a delta G of negative 205.2 kilojoules. Now, this is negative, meaning the reaction is spontaneous. If delta G is negative, the reaction is spontaneous.